Hey there, Algebra 2 students, Mr. Weber here. Today we're going to talk about independent and dependent events. Okay, so events are independent if the occurrence of one event does not affect the probability of the other event. So if you have two things that are happening, and when you do the first event, if the probability of the second event does not change, then we say that those two events are independent. For instance, if I flip a coin and I roll a dice, okay, when I flip the coin, that coin is going to have no impact on the dice. So the probability of me rolling a 6 on the dice is going to be the same, whether I flip a heads or a tails on the coin. The coin is not going to affect the probability of the die. Does that make sense? Okay, so that's an independent event. Two events where the probability, where the actual event does not change or affect the probability of the other event. Okay, so the formula for doing that is if we have two events A and B and they are independent events, then the probability of both occurring is the probability of A and B is equal to the probability of A times the probability of B. Okay, here's what you're going to have to think about. Multiple events means we multiply. Okay, what you're going to have to think about is what are those probabilities of the multiple events? But multiple events means we're going to multiply our probabilities together. And that's the heart of what you have to do today. Okay, look at example 1. A coin is tossed twice. Find the probability of tossing heads twice. All right, so here's my question. If you flip a coin, does flipping that coin and the outcome of one flip, does that affect the probability of the second flip? And the answer is no. The probability is going to stay the same because each time you flip the coin, it's independent of every other event. So probability of getting a heads and a heads is going to equal to the probability of getting a heads times the probability of getting a heads. Now, what's the probability of flipping a coin and having it land on heads? That's 1/2. So what we're thinking about here is 1/2 times 1/2. Remember how we multiply fractions? We're just going to multiply these straight across. So 1 times 1 is 1, 2 times 2 is 4, and our answer is 1/4. Sound good? Look at number 2. A number cube is tossed twice. Find the probability that A, the first number, is greater than 2, and the second number is even. Okay, so is the probability of one of these tosses going to affect the other? No. A number cube, or a die, is just like a coin. Every time you roll it, it's going to be independent. The sides aren't changing. It's not like you all of a sudden have 5 sides instead of 6 sides. You're always going to have 6 sides. Those sides aren't going to change, so the probability is going to stay the same, regardless of how many times we roll that die. Okay, so here we go. So let's think about this. So here we are, the probability that we get a number greater than 2 times the probability that it's even. Well, let's think how many numbers on a number cube, and we're going to assume that the number on this number cube is 1 through 6. That's always a safe assumption unless they tell you otherwise. So if it's a regular die, a regular number cube, 1 through 6, how many numbers are greater than 2? Do we count 2? No, we do not. So we could roll a 3, we could roll a 4, we could roll a 5, or we could roll a 6. All right, so there's 1, 2, 3, 4 things that we could roll, which means the probability would be 4/6. Okay, what about the probability that we get an even number? Well, how many even numbers are there? 2, 4, and 6. So our probability here should be 3/6. So what we're looking at here is 4/6 times 3/6. We'll multiply straight across again. And we'll get 12 over 36. And then we can use our calculator or just divide top and bottom by the same number, say 12. And the answer should be 1/3, or 0.033 repeating. Are we good? All right, let's try B. Probability that the first number is a 4 and the second number is less than 3. All right, so let's think about our options. How many 4s are there? Only 1. So that probability should be 1/6. How many numbers are greater than, or I'm sorry, are less than 3? Well, we could get a 1 or a 2. Can we count 3? Nope, we can't count 3 because it's not equal to, it's just less than 3. So here we have 1/6 times 2/6. We multiply straight across. And we get 2/36, or 1/18. All right, does that make sense? I hope that it does. Okay, so if you want to pause the recording and try to do number 3 on your own, that'd be a great place to see if you're starting to get this. And as soon as you're ready, hit play and we'll go through it. All right, so a jar contains 2 red marbles and 3 green marbles. 1 marble is selected at random and replaced. Then a second marble is selected. Find the probability. Okay, this is super important, this idea of it being replaced. So let's think about this. So if I have a jar, see my fancy jar there, and I fill this fancy jar with green marbles. Let's say I have 3 green marbles. 1, 2, that's an awesome circle. I could have been an artist, guys, you know that? And I got some red marbles in here. 2 of those. All right, how many do I have? I have 5 marbles inside my jar, right? Okay, now let's say that I pick one randomly. I'm going to randomly pick one. Let's say it's one of the red ones. All right, so now I have a red one out here, and I no longer have a red one on the inside. Look at that, magic. Okay, now, if I were to select my second marble while that red marble's still out, look what happens. The number of marbles in the jar has changed, and the number of red marbles has changed. So my probability has changed. However, what are they telling me to do? They're telling me to replace it. That means I take this red marble that's out and I put it back inside. So now it's no longer outside. Does that make sense? So when I draw the second one, look, I still have 3 green marbles. I still have 2 red marbles. So these are independent events. That's the first thing you have to understand, is these are independent events because we've put that marble back into the jar before we select that second marble. So nothing has changed. Okay? So we're looking for the probability of of green times the probability of red. Well, how many green marbles are there? Only 3. How many total marbles are there? 1, 2, 3, 4, 5. So it would be 3 out of 5. What about red marbles? Well, there's only 2 red marbles. So that's 2 out of 5. So the probability of green marbles times red marbles is going to be 3/5 times 2/5. 3 green marbles, 2 red marbles, 5 total. Are we okay? All right, I hope so. All right, so now let's just do our math. Let's just multiply straight across. 6/25. Done and done. Okay, now that we know that they are independent events, we can roll through B and C pretty quickly. All right, so we want the probability of a red marble times a red marble. Well, what's my probability of a red marble? 2/5. My probability for a green marble would be 3/5. All right, so I want a red and then a red. This is going to be 2/5 times 2/5, and then I can multiply straight across. Which is 4/25. All right, look at C, the probability that both are green. Well, the probability of a green marble is 3 out of 5. So I want the probability of green times green. That's going to be 3/5 times 3/5, which is going to be 9 over 25. So far, so good? Okay, here we go. 4. Events A and B are independent if the probability of A is 0.2 and the probability of B is 0.7. What is the probability of A and B? This is a great type of question that I've seen questions like this on final exams and on SAT questions because this is just a straight up, do you know how probability of independent events work? So let's think about what we know from the very beginning in our notes. Probability of A and B is equal to what? Multiple events means we multiply. So it's the probability of A times the probability of B. Well, they tell us, what is the probability of A? That's 0.2. What is the probability of B? That's 0.7. So all we have to do is multiply 0.2 times 0.7. Grab your calculators. Beep, boop, 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 beep, boop, boop, boop. 0.14. Done and done. Okay? All right, look at 5. 5's a little bit tricky. If you think you got 4 and you try 5, it's very possible you get kind of mixed up, and that's okay. All right, because guess what we're doing? We're learning. All right, so events C and D are independent. If the probability of C and D is 0.08 and the probability of D is 0.5, what is the probability of C? Okay, this looks very similar, but look at the difference. So in number 4, they gave us the probability of A and B, and they asked us for the probability of A and B. They asked us basically for the answer to this equation. But look, in number 5, they give us the answer. They're asking us to find one of the input values. So as a teacher, if I ever want to make a question a little bit harder, this is what I do. I give you the answer and I ask you to work backwards or to solve for one of the input values. It's one extra step and you guys can do it, okay? Don't get tripped up on it. Think about what you know. The probability of C and D is going to be equal to the probability of C times the probability of D. All right, let's think about what we know. The probability of C and D is 0.08. The probability of D is 0.05. All right, what we still don't know is the probability of C. So how are we going to get there? Well, look at the operation. This is a simple one-step equation. What's the operation between that probability of C and the 0.5? It's multiplication. So what I really want to do is solve for the probability of C. I want to solve for that variable that's missing. So all I have to do is the opposite of what I see. I see multiplication. So what do I have to do? Division. So we're going to divide by 0.05. That should cause the 0.05s to cancel, and we'll end up with the probability of C. Does that make sense? But whatever we do to one side, remember we have to do to the other side. So grab your calculators. 0.08 divided by 0.5, and that's the probability of C. 0.16. Is that okay? Done and done? Okay. Now, those were independent events. Now we're going to talk about dependent events. All right, so if you know an independent event, then a dependent event is just the opposite. So events that are dependent events, they are dependent events if the occurrence of one event affects the probability of another. What does that mean? It means that the probability of the second event will change after the first event takes place. All right, think about our example with the marbles. When we took that marble out, the probability inside changed because the number of total marbles was now one less. That's what we're talking about. So when you have an event and the second event changes the probability of the first, that's a dependent event. This is very similar to what we talked about when we did the fundamental counting principle, when we saw that as we selected a person, like if we were selecting first, second, and third place from a class, after we selected one person, then we had less people to choose from, so the numbers went down. A similar thing is going to happen here. That's the big idea behind a dependent event. So once the first event takes place, it alters or it affects or it changes the probability of that next event. So we have to account for that. All right, so there's going to be some key words in the problem that you're going to have to look for. All right, when you see the word is replaced, all right, is replaced, that means they're independent. And if they're independent, then our probability, let me get a different color here. If they're independent, the probability does not change. Okay? If they say something is not replaced, that means we're talking about dependent events, and that means that our probability will change. All right, so in both cases, we can think about multiple events means we multiply. Okay, multiple events means we multiply. Let's see how it works. Okay, so here we go. A jar contains 2 red marbles and 3 green marbles. 1 marble is selected and not replaced. Then a second marble is selected. Find the probability that. Okay, so I'm going to draw a quick little diagram again. We have our cup. There's going to be 2 red marbles inside here. And there'll be 3 green marbles inside here. That one's flat. Okay, so if we take the probability, look at A, the first marble is green, the second marble is red. Okay, so if we take a green marble, and let's say that we select a green marble from this jar. All right, so there's 1, 2, 3 red marbles. So the probability before we get started would be 3 out of 5. Okay, so that part makes sense. But if we were to take a green marble out, look at what's going to happen. Now, 2 things have happened. Okay, so I want to find the probability of green times the probability of red, given that a green's already taken place. Okay, so how many marbles are left? Now there's only 4 marbles left. And how many of those are green? Only 2. So the probability of our first selection is 3 over 5, like we expect. But when we draw our red marble, okay, there's 2 red marbles and only 4 marbles left in the jar. All right, so the probability of drawing a red marble is 2 out of 4, not 2 out of 5. All right, we're still going to multiply straight across. We get 6 over 20. We can simplify that to 3 over 10. Okay, look at B. Probability that both marbles are red. All right, so how many red marbles are there? Let me go ahead and put this green marble back inside. There's a green marble. Now what am I doing? I'm going to draw a red marble. So let's draw a red marble. We take a red marble out. So the probability that I draw a red and then a red, well, the probability that I get a red off the top is going to be 2 out of 5. All right, because there's 2 red marbles and 5 total marbles in the jar. All right, however, once I draw that first one, look at what happens. Now, how many total marbles are left? Only 4. And how many are red? Only 1. So the probability of the second selection, even though they're both red, our probability has changed. It's changed because we did not replace this first marble. This first marble is sitting out here outside of the jar. Okay, that affects our probability. We're still going to multiply straight across. We're going to get 2 over 20, which simplifies to 1 over 10. If you think you got it, you can go ahead and pause it and try to do the number C on your own. Number C. Okay, so right off the bat, when we draw our first green marble, the probability is going to be 3 out of 5. But then what's going to happen? Okay, so once we take that green marble out, there should be only 4 marbles left. And I should have 1 less green marble because the first marble was green. So I started with 3 green marbles. Once I took 1 out, now I only have 2 green marbles left in the jar. Does that make sense? Multiply straight across, 6 over 20, which is 3/10. It's the same answer to A. Yeah, it worked out. All right, does that make sense? Okay, so here we go. Number 7. We have 8 balls numbered 1 through 8 in an automatic random selector, kind of like the NBA draft. And a ball is selected at random and is not replaced before the second ball is selected. That means these are going to be dependent events. That means our probability is going to have to change. All right, so find the probability that the first number is odd and the second number is even. Let's think about how many odd numbers there are in the numbers 1 through 8. We have 1, 3, 5, and 7. 1, 3, 5, and 7. How many even numbers are there? 2, 4, 6, and 8. So I have 4 odd and 4 even. All right, so the probability that I select an odd number is going to be 4 over 8. However, once I select that first ball, okay, how many balls are going to be left in the random selector? Now only 7. So our denominator should go down by 1. There's still 4 because there's 2, 4, 6, and 8. None of those were selected. One of these got selected. Let's say it was the 3, just for instance. All right, I still now have 7 I can choose from, and 4 are even. All right, multiply straight across. 16 over 56, which simplifies to 2 over 7. Okay? All right, let's look here. The probability of the first number is a 4. How many numbers are a 4? Just 1. The second number is less than 4. That means it could be a 1, a 2, or a 3. All right, so the probability that I select a 4, that's going to be 1 over 8. But when I select that second one, because I've already taken 1 out, then the probability has changed. Now there's only 7 balls left, so it's 3 out of 7. Multiply straight across. We're going to get 3 over 56. All right, does this make sense? I hope that it does. Let's look at C. Both numbers are even. Both numbers are even. All right, that means it's going to be a 2, a 4, a 6, or an 8. That's an awful 6. 2, 4, 6, or 8. All right, so the first selection is going to be 4 out of 8. However, once I choose one of those numbers, let's say I get that 6 out of there, now there's going to only be 3 left. So probability of the first event was 4 out of 8, but because one of those balls were out, now there's only 7 left, and only 3 of them that are left are going to still be even. So it's 3 out of 7. Multiply straight across. 12 over 56, which simplifies to 3 over 14. And that, my friends, is independent and dependent events. The last thing you're going to have to do is read a situation and be able to tell, is this an independent or a dependent event? Okay, so you want to go ahead and pause it. Try to answer 8 through 12 on your own. You can just put an I for independent or a D for dependent, and then hit play, and then we'll talk about each one. Okay, a coin comes up head, and a number cube is rolled at the same time, comes up 6. All right, so here's the question. Did flipping the coin and having it land on heads, did that affect the probability of this die becoming a 6? And the answer is no, because a coin and a dice are not going to affect each other at all. Okay, so that's an independent event. So flipping that coin has no effect over whether that die comes up 6 or not. Okay? Number 9, a 4 is drawn from a deck and set aside, and then an ace is drawn. All right, so the key here is that it's set aside. So because it's set aside, it's not put back in the deck, which means that there are not 52 cards still in the deck. There's now only 51. So that's going to be a dependent event. A dependent event. All right, number 10. A 1 is rolled on a number cube, and then a 4 is rolled on the same number cube. Well, think about that. The cube's not going to change when you roll it. Doesn't matter how many times you roll it, the number of sides are still going to stay the same. The number on each of those sides is not going to change with every roll. So that's an independent event. Okay, 11. I'll be honest, I don't like 11. I'm going to put both answers on here. I don't think it's very clear. All right, so a dart hits a bullseye and a second dart also hits 20. I'm sorry, I didn't read this question clearly enough. These are independent events. Weber. All right, so this should clearly be independent. Okay, because they're hitting two different sections on the board. That's my fault. I apologize for that. I thought they hit the same section. So they're hitting two different sections on the dartboard. So one dart hits the bullseye. The amount of area that is a 20 is not going to change. So these we'll say is an independent event. Okay. Okay. Number 12. A bag of contains the slips of paper 1 through 9. Selecting 2 even numbers when 2 slips are chosen without replacement. All right, 2 are chosen without replacement. All right, so the key here is that they are not going to replace without replacement. That means the probability should change. This is a dependent event. Okay, does that make sense? And that is it, my friends. You have done independent and dependent events. If you have questions over any of this stuff, please reach out to your teachers. We'll be happy to help you. And you know, I just want to say thank you for all the hard work you guys have done. You've done a great job through all of this, and all your teachers, myself included, are very, very grateful for each and every one of you. So thank you guys so much. I love you all. Have a good one.